Welcome everyone. My name is Dr. Simphiwe Mphuthi from the University of Cape Town in the Dramatics Division. Today I'll be giving you a presentation on Africa's contribution and integration into the global reference frame, specifically into the International Height Reference Frame and the International Terrestrial Reference Frame. This presentation will be given for a virtual school of geodesy. This presentation highlights both the progress made and the challenges faced on the continent using South Africa as a case study. Africa is undergoing significant transformation in geodetic infrastructure. However, despite global advances, many African countries still operate in isolation from international systems. This presentation aims to spotlight Africa's strategic roles and the steps being taken towards integration with the International Reference Frame and the International Terrestrial Reference Frame. Objectives of this presentation. The objectives are to clarify what International Height Reference Frame and International Terrestrial Reference Frame are. It also explains why Africans' participation is essential. It also examines current challenges with geodetic data across the continent. It also showcases progress made in South Africa and also proposes pathways forward for broader continental integration. What is International Height Reference Frame and International Terrestrial Reference Frame? The International Terrestrial Reference Frame provides a global coordinate reference system based on GNSS and space geodetic techniques, and the International Height Reference Frame complements this by providing a global vertical reference frame based on gravity-related heights. Both are vital for precise positioning, infrastructure planning, and also conducting scientific researches. Importance of Africa's participation. Africa's integration is critical for completing the global geodetic network and also for supporting regional development like water and resource management and infrastructure, also for providing supports for SDGs and disaster monitoring, filling large gravity data voids, which limits the accuracy of the global geoid models. Now let's look at datums, which are common challenges across African countries. Many African nations still use outdated datums like the clock 1880. These legacy systems are not compatible with the IHRF or the WGS84 ellipsoid. They also provide the limited geodetic infrastructure like sparse control networks and GNSS space stations, and they further complicate the datum monetization. Beyond infrastructure, challenges also include the lack of trained personnel and limited funding. Continued reliance on external supports, absence of unified vertical datum complicates integration of elevation datasets across borders, and development of other major challenges include data hoarding and poor sharing between institutes. Transformation parameters are often missing or incorrect, leading to positioning errors when switching between datums. Now let's look at the influence of South Africa towards the development of a geodetic datum across the continent. The Cape datum was developed in the early 20th century using the modified Clock 1880 ellipsoid. I'm sure most of you are familiar with that, and it served as the basis for the country's triangulation network. Importantly, it influence extended well beyond South Africa, especially along the 30th meridian, where it was used for regional triangulation and mapping projects across Southern Africa. Many countries such as Botswana, Zimbabwe, and Zambia adopted this framework, and which provided a uniform reference system at that particular time, but later became outdated. However, it is still in use in some of the countries situated on the Southern African region and also on the Eastern African region. Just to add a few, Cape datum was non-geocentric, and it was also not, of course, it was not aligned with global datum like the WGS84 or the IHRF. Even though there are still some of the countries in the stated regions that are still using the outdated datum. Now let's take a look at South Africa as a case study with regards to modernizing the geodetic datum. The Hartepies Hoek 94 coordinate system became the official system in South Africa on the 1st of January 1999. This system superseded the previous Cape datum system or coordinate system, and it was in alignment with the IHRF. Basically, the new system was based on the IHRF 1999 or IHRF 91, Epoch 1994 coordinates for the Hartepies Hoek Radio Astronomy Observatory, and it used WGS 84 as its reference system. South Africa also has an active GPS course network stations, which are referred to as TrickNet. It has over 60 GNSS course stations distributed across the country to support precise positioning and transformation. The distribution of this GPS course stations is as indicated on the figure at the bottom right rather. Okay, now let's look at the vertical datum side or the vertical side. In South Africa, we use the land leveling datum, or our vertical datum is referred to as land leveling datum, or LLD in short. It is based on the 4 tout gauge benchmarks, which are located in Cape Town, Durban, East London, and Port Elizabeth. Our land leveling datum was established in the 1900s, which is more than 100 years ago, using the mean sea level data from the 4 tout gauge benchmarks which are mentioned above. It is associated with a number of issues, such as inconsistent leveling networks, which were adjusted independently. The land leveling datum has been approximated to be 15 to 20 centimeters below the mean sea level. Of course, such a datum is disconnected from the global vertical datum or from the global vertical frameworks like the IHRF. In South Africa, we also have a hybrid quasi-geoid model that we used solely for the purpose of transforming ellipsoidal height to the version of orthometric height that we use in South Africa, which is referred to as spheroidal orthometric heights. This quasi-geoid model was developed by Prof. Mary in 2009. However, it was formally established or formally used in the country in 2010. Currently, there are a number of approaches or attempts to develop the geoid-based vertical datum for South Africa. Just to mention a few current studies, the first study which was done was to conduct a relationship between the vertical datum, to determine the vertical datum offsets to the international height reference system, which was estimated in South Africa, and also to determine a suitable height system for South Africa, which is in line with the geoid-based vertical datum. All these studies are conducted for an attempt to move towards a geoid-based vertical datum for South Africa, and also to develop a unified vertical datum for South Africa in order for us to participate on the international height reference system, or to be in line with the international height reference frame. Aligning with the international height reference frame, still using South Africa as a case study. This will require the vertical datum that is associated or that is attached to a geopotential number or geopotential value. This will make it possible for obtaining or measuring physical height using a GPS system or satellite-based surveying instruments, rather than measuring the geometric heights as it is the case currently. The difference between the physical height and the geometric height, it's solely based on physical height. It's height that can define the flow of water, and the geometric height, that's just a height system that is based on an ellipsoid. Our current height system, which is a spheroidal orthometric height, is more aligned or more in alignment with the normal height system, which is referenced from the quasi-geoid model. IHRF integration involves maintaining a GNSS infrastructure, ensuring data quality, and aligning national datums with global ones. TrickNet plays a key role in this case, but long-term consistency and regional cooperations are equally important. Of course, this can be conducted through supports from communities such as IHRF and ITGRF. There's quite a number of challenges that are remaining, such as limited human and financial resources, fragmented data management, and the need for more regional collaborations and standardization in vertical data development. There should be a way forward to deal with the previous challenges, such as developing national geoid models in alignment with the IHRF, and also strengthening regional cooperation, establishing open data policies across countries in Africa, and also investing in human capacity throughout training and educational programs. I've drawn quite a few conclusions from integrating Africa into the global reference system. Africa's integration into the International Height Reference Frame and the International Terrestrial Reference Frame is not just possible, it is quite essential. South Africa is laying the ground, but the broader continent must follow with support from the international agencies, regional initiatives, and national commitments. Of course, as this has been summarized from this presentation, that the key challenges include the legacy systems, limited gravity data, and the absence of unified vertical datums, and also the capacity building across border collaborations and data sharings are quite vital. Aligning with the global standards supports sustainable developments and infrastructure planning and scientific advancement. These are a few references that I've used to compile this presentation. Thank you for your attention. I welcome your questions and look forward to the discussion. Please feel free to reach out to me via this email or email provided below for any follow-up queries. Thank you.